All right, friends, so here comes the second part of this video, focus topic being straight line motion. So this problem has come from a person called the Master Math Mentor. God, I love that title, and I want that to be mine. So the situation is we have a searchlight trained on the intersection of a building and a wall. At time t equals 0, the light travels along the wall in a straight line. For 0 less than or equal to t less than or equal to 20, the velocity of the light is modeled by the piecewise function defined by the graph below. The graph is made up of lines and a semicircle. Okay, so before we do anything else, I think it's important to understand the situation. We have a searchlight, so like a spotlight, shining where the building and the wall come together. The graph below represents the velocity of the searchlight over time. So we're going to have the searchlight. If we look at this first part of the graph, at time t equals 0, we have positive velocity. Since we have positive velocity, the searchlight is going to be moving to the right. As we move towards t equals 3, this is where the velocity is a maximum. That means that's where the searchlight is moving as fast. That's its greatest velocity. That's when it's moving as fast as possible. And then the velocity starts to decrease, still moving to the right. The spotlight doesn't actually change direction until right over here. So with all of that said, let's look at a couple of the questions that the Master Math Mentor put together. Question A asks the question, at what times in the interval 0 less than t less than 20, if any, does the light change direction? Let's see. So what I know is in order for the light to change direction, the light is going to the right, and then it starts to come back to the left. When I'm moving to the right, my velocity is positive. When I'm moving to the left, my velocity is negative. So in order for the light to change direction, what this means is that the velocity has a change in sign. Where do we have a change in sign? Let's look at the graph. I see over here at t equals 7. The velocity changes, and how does it change? It changes from positive to negative. Where else does it change? Over here at t equals 16. The velocity changes from negative to positive. So at t equals 7 and at t equals 16, the searchlight changes direction. Done. That's it. Probably just a 1-point question, maybe 2 points. The first point could be from your showing that you know that if for the searchlight to change direction, the velocity has to change sign. After that, the second point, if it is a 2-point question, would probably come from indicating t equals 7 and t equals 16 and the change that we're seeing there. Okay, so that's part A. That's pretty easy. Let's try part B. Part B, at what times in the interval 0 less than or equal to t less than or equal to 20 is the light farthest from the building? How far is the light from the building at this time? The key phrase here is I want the light to be farthest from the building. If the light is farthest from the building, then what that means is that the displacement, displacement is change in position. So the searchlight is farthest from the building when the displacement is greatest. Now, how do we find displacement? We find displacement by integrating velocity with respect to time from some point to some point. If I wanted to know the displacement from time A to time B, I integrate the velocity from A to B. Well, if I want greatest, what really we're talking about over here is as soon as I see that word greatest, I know that we have to look for an absolute maximum. With an absolute maximum, in my class we have a 4-step process. So step 1, we identify the candidates. Where could we have an absolute maximum, where would the displacement be greatest? Well, over here at t equals 7, the searchlight changes from positive velocity, that means searchlight is moving forward, to having negative velocity, the searchlight comes back. If over here is that intersection of the building and the wall, we've been moving forward until t equals 7. At t equals 7, we come back, and we keep coming back until t equals 16, at which point we turn around. My candidates for absolute maximum, therefore, are at t equals 7 and t equals 16. Those are my candidates. Next is I need to evaluate the displacement. I need to evaluate displacement at t equals 7 and t equals 16. So in order to find the displacement, I'm going to find the integral from 0 to 7, v of t dt. That'll be the displacement at 7. I need to evaluate the displacement at 16. So we're going to do an integral from 0 to 16, v of t dt. We're going to get answers for those. After we've evaluated the displacement, after that we need to evaluate the endpoints. Okay, the endpoints for the interval they're interested in are 0 and 20. So I'm going to need to find, let's see, the displacement from 0 to 0, v of t dt. Well, that's equal to 0. And I'm going to need to evaluate my displacement from 0 to 20, v of t dt. Some work is going to need to be done there. And then finally, I'm going to need my conclusion. We're going to have to write a sentence that answers their question. All right, so now that we've laid that out, let's actually go through and let's evaluate. And actually, let me back up on this thought. If I was in the middle of the AP exam, as soon as I've identified that it's the 4-step process and I need to find candidates and I want to evaluate the displacement, I would probably write everything on my paper just like I did right here, and then later on go back and figure out, okay, well, what is this displacement? I want to show the AP graders as quickly as possible, hey, I know what's going on. I've got a good process here, and there's possibilities of earning points for showing that you really, truly understand how to show an absolute maximum. Like I said, it's a possibility, it's not a guarantee. So I want to find the integral from 0 to 7 v of t dt. I'm going to zoom in on the graph a little bit here. If I want to find the area starting at t equals 0 and going until t equals 7, that's right here, well, I need to break this region into sections that I know. Well, I was told that there's a semicircle. I can kind of see the semicircle piece, so let me cut it right here. If the section above this line is a semicircle, well, I'm going from t equals 0 to t equals 6. My diameter is 6. My radius is 3. Since the area of a circle is pi times r squared, I'm going to have pi times 3 squared. Since we only have a semicircle, we divide by 2. What else do we have? Well, the region underneath that line, I could look at this as a trapezoid, or I could look at it as a rectangle followed by a triangle. I'm going to go with the rectangle triangle. We have a length of 6, we have a height of 2, so that area is 12. This little region in here is a triangle, 1/2. The base is 1, the height is 2, that's 1. So let's zoom back out here. If I want to talk about the displacement, I'm going to take 9 pi over 2 plus 12 plus 1, and I can make that 9 pi over 2 plus 13 if I'd like to. That's the displacement at t equals 7. To determine the displacement at t equals 16, now we go back to our graph and we're going to go from 0 all the way over here to 16. Well, what's new? We already know all this mess over here is 9 pi over 2 plus 13. The new piece is this area between 7 and 16. I can see that it's a trapezoid. The area of a trapezoid is 1/2 base 1 plus base 2 times the height. This is a base. This other horizontal piece is the base. The first base goes from 7 to 16, so that has a length of 9. The second base, it seems to start over here at 9 and at 12. That has a length of 3. The height, let's see, if I start on the x-axis, I drop down to -4. The height is 4. Add your bases. 9 plus 3, that's 12. Times your height is 48. Cut it in half. 24. Be careful, since we're below the x-axis, that's -24. So when I come back and I find my displacement, we're going to have 9 pi over 2 plus 13 minus 24. That's going to be 9 pi over 2 minus 11. Check. All right, we already know the value of the endpoint. The displacement from 0 to 0 is 0. The displacement from 0 to 20, last thing, I go back to my graph. We've already figured out all of this area. We've identified all of that area. The last piece is to go from 16 to 20, which is a nice, easy triangle with a base of 4 and a height of 4. 4 times 4 is 16. We cut that in half. We get positive 8. So my displacement is 9 pi over 2 minus 11 plus 8, which is just 9 pi over 2 minus 3. Now, before you wrap this up, before you give yourself a high five for being a super smarty, make sure you answer the questions. The original question said, at what time in the interval is the light farthest from the building? Well, at what time is the displacement greatest? Is it 9 pi over 2 plus 13? Is it 9 pi over 2 minus 11? Is it 0, or is it 9 pi over 2 minus 3? And although I may not know what 9 pi over 2 is exactly as a number, and that's okay, I know that if I add 13 to that, that has to be bigger than taking that 9 pi over 2 and subtracting 11. It's probably bigger than 0, since 9 pi over 2 and 13 are positive. And it's probably bigger than 9 pi over 2 when I subtract 3. So I would say farthest, my conclusion, farthest from building at t equals 7. And then let's answer the second part. The distance is 9 pi over 2 plus 13. Since no units were mentioned in the problem, I'm not going to make up my own units. I'm just going to leave that as my answer. Congratulations, you've just survived what is the hardest part of, I think, this entire question. But let's move on. Part C, same graph. Find the total distance the light travels during that time interval. Total distance. What do I know about total distance? The formula for finding total distance is, it's almost the same as displacement. We're going to do an integral from a point to a point, but instead of integrating the velocity function, we integrate the speed function, so we need absolute values. So in this case, I want total distance on the interval 0 to 20. So I'm going to integrate from 0 to 20 the speed function, v of t dt. In order to do that, the only thing that changes, the distance, if this graph here is velocity, speed means we take the absolute value. So you can flip this little trapezoid up. Okay, it should be a perfect reflection. It's now above the x-axis. Find the total area. We know from earlier computations from 0 to 7, that has a total area of 9 pi over 2 plus 13. The trapezoid, when it was below the x-axis, had an area of negative 24. So that's positive 24. And this little triangle that stays the same has a grand total area of 8. So my total distance traveled, 9 pi over 2 plus 13 plus 24 plus 8. That's the same as 9 pi over 2 plus 45. You don't have to go all the way to here. This is the total distance. But so is 9 pi over 2 plus 13 plus 24 plus 8. There's no need to simplify. And in fact, you run the risk, if you incorrectly add these numbers, Even though you've done the right thing, you lose the final answer point. I'd hate to see that happen. All right, part D. This was a new question for most of my students. Write expressions for the light's acceleration, the velocity, and the distance from the building that are valid for the time interval 6 less than t less than 9. So first of all, let's make sure we understand this. I only am interested in the time interval 6 to 9. So if I were to zoom in, or I kind of like to think of it as putting my blinders on. If I'm only interested in the part of the graph between 6 and 9, I need to come up with equations that represent the velocity on that interval, that represent the acceleration on that interval, and that also represent the position on that interval. Well, let's see. What's the velocity? Since this is the graph of velocity, for the time interval 6 less than t less than 9, the velocity is just a straight line. The way I find the equation of a straight line, I need one point, I need one slope. See, this point over here should do nicely. I can see pretty clearly that that's the point 6, 2. To find the slope, I need another point. How about this guy over here? This is the point 9, -4. To find the slope, I do rise over run, so I'm going to go down 6. I'm going to go right 3. The slope is -6 over 3, which is -2. So I'm going to write my velocity as my slope, -2, parentheses, not x minus 6, t minus 6, plus 2. Or, if you'd like, you could say that your velocity is -2, t minus 9 minus 4. Or, if you'd like, you could distribute that -2 and say it's -2t plus 18 minus 4 is plus 14. It really doesn't matter. Any one of those are perfectly valid answers. Leave it alone. All right, now I need acceleration. What do we know about the relationship between velocity and acceleration? I know that the acceleration is the derivative of the velocity. Okay, I need to take the derivative, so we're taking a derivative with respect to t of my velocity equation. Let's go with the -2t plus 14. The derivative of -2t plus 14 is -2. That's your acceleration. Good. We've got the velocity, we've got the acceleration. I suspect this is probably a 3, maybe a 4-point question. I would expect students would be awarded 1 point for velocity. They'd be awarded 1 point for determining the acceleration. The work comes in determining the distance from the building, or the displacement. If I want to figure out the displacement, well, let's see. The displacement at time t is going to be the integral from 0 to t of the velocity function. That's the displacement. What we know about t is that t is some number between 6 and 9, because we're looking for expressions that are valid on this time interval. So whatever value of t we're looking at, it's at least 6, but it's no more than 9. What that allows me to do is I can say, well, let's actually break this up into 2 different intervals. Let's look at this expression as the integral from 0 to 6, v of t dt, plus the integral from 6 to t of v of t dt. And technically I'm using bad notation here. I'm using t in my integrand. T is my limit of integration. I really shouldn't be doing that, but we're just going to kind of let that slide right now. It's bad notation. It's not wrong. It's just bad notation. All right, so let's see. This over here, the displacement from 0 to 6, is just a measure of the total area from 0 to 6. We've already done that because that doesn't include the triangle. This front part is 9 pi over 2 plus 12 plus On the interval 6 to t, as long as t is between 6 and 9, I already have an expression for my velocity. That's this negative 2 plus 14. I need to integrate that with respect to t. Kind of running out of room here, so we need a little more paper. So let's keep going with the computations. We have 9 pi over 2 plus 12 plus the integral of negative 2t plus 14 is negative t squared plus 14t. We need to evaluate that between 6 and t. All right. 9 pi over 2 plus 12. Plug in t, you're going to get negative t squared plus 14t minus, evaluate the function at 6, negative 6 squared plus 14 times 6. And as far as I can tell, everything else at this point is just algebraic simplification, which means it doesn't need to be done. You just want an expression in terms of t, and we have it. So my advice to everybody is stop right there. You're done. For those of you that are tempted to do some simplifications, or you just like showing off your algebra skills, great, let's go further. 9 pi over 2 plus 12 minus t squared plus 14t minus, let's see, 6 squared is 36. Make that negative. 14 times 6 is 84. So we've got 9 pi over 2 plus 12 minus t squared plus 14t. Negative 36 plus 84 is 48. We're going to subtract 48. I can combine like terms, 9 pi over 2. Positive 12, negative 48 is negative 36. Negative t squared plus 14t. But all this work that you did after the point where I indicated stop, none of it's calculus. It's number. It's number skills. We're squaring 6. We're multiplying 14 and 6. Great. If you just have to do this because you don't feel complete unless you get the most compact answer, that's fine, but it truly is a waste of your time. And if you make a mistake somewhere between here and down here, you're going to lose the point that you used to have up here. So with that, that ends the video on straight line motion. These are two of the most challenging physics questions I could find at this point. If I find any others that I think are worth recording, I'll definitely do that. But over the next couple of weeks, I'm going to focus on some of the other heavy-hitting topics. And I hope that helps out. Good luck.